Every single year, over 30 million tons of bamboo are harvested across the world. That's more than the combined weight of all the commercial airplanes ever built. But bamboo isn't just any plant. In fact, it's not even technically a tree, it's a grass. And not just any grass. This is the grass that can take on steel, silk, and even concrete. It's a plant that can grow taller than a giraffe in a matter of weeks, absorb more carbon dioxide than a forest, and regenerate itself without anyone planting a single seed. Bamboo isn't just another green stem waving in the wind. It's a green giant quietly revolutionizing industries, from construction to fashion. And this journey begins in places where acres of these towering stalks stretch as far as the eye can see. These aren't wild, overgrown thickets. Bamboo plantations are carefully managed, functioning more like sustainable farms than forests. Unlike trees that take decades to mature, bamboo grows rapidly and regenerates naturally. When a stalk, known as a culm, is cut, it doesn't need to be replanted. Thanks to its underground rhizome network, new shoots sprout almost immediately, allowing the same plantation to produce for decades without exhausting the soil. Bamboo stands out not just for its growth, but for its environmental benefits. It absorbs 35% more carbon dioxide and produces 35% more oxygen than an equal area of trees, making it a powerful ally in the fight against climate change. It thrives without chemical fertilizers or replanting, making it one of the most renewable resources on Earth. Harvesting bamboo is a precise task. Only mature stalks, aged 3 to 5 years, are selected based on color and texture. Workers use machetes or handsaws to cut them, leaving younger shoots untouched to continue the cycle. These towering stalks, sometimes 60 feet tall and weighing over 100 pounds, are then transported, often by hand-loaded trucks, to processing plants. What happens next is an industrial transformation that turns this green giant into flooring, fabrics, and so much more. The journey of bamboo from stalk to product begins with chopping down the towering green culms into smaller, manageable pieces. These sections are then fed into powerful machines that split the rounded stalks into flat, usable strips, each one cracking open with a loud, unmistakable snap. This is the moment when bamboo stops looking like a wild plant and starts to resemble a raw material ready for engineering. But raw bamboo isn't ready for use just yet. The outer green skin and inner nodes must be stripped away, revealing a pale plank underneath. However, inside that plank are sugars and starches, exactly what mold, fungi, and insects love. To make bamboo last, these must be removed. The planks are soaked in large vats filled with boiling water or hydrogen peroxide, a sterilizing bath that kills bacteria, draws out sugars, and leaves the bamboo clean. Moisture is the next challenge. Raw bamboo holds up to 50% moisture, so it goes into industrial kiln dryers until that level drops to a stable 8 to 10%. Once dried, it's milled into perfect rectangles. These planks can be laid flat for horizontal flooring or turned on their edge for denser vertical flooring. But strand-woven bamboo goes further. The bamboo is shredded into fibers, mixed with eco-resin, and pressed under 3,000 psi. The result? A block of material that can score over 5,000 on the Jonka hardness scale, far tougher than oak. Surprisingly, bamboo also transforms into ultra-soft fabric. Ground into pulp, chemically treated into viscose, and extruded through fine nozzles into acid baths, it becomes silky, breathable thread. That thread is then spun into fabric that's hypoallergenic, antibacterial, and perfect for everything from clothing to bedding. From hard as oak to soft as silk, bamboo truly does it all. Bamboo's dual nature, strong as steel yet soft as silk, has made it a favorite across industries. It's in cutting boards, textiles, scaffolding, and even luxury car interiors. What makes it extraordinary is that it grows faster than any tree, needs no chemicals, and regenerates on its own. From paper and furniture to biomass fuel and construction, bamboo is everywhere. With over 1,000 species suited to different climates and uses, it's cultivated globally, from Asia to Africa and South America. The bamboo industry is now worth over $100 billion and continues to grow. Whether it's scaffolding that bends without breaking or sleek, sustainable flooring, bamboo blends beauty, strength, and environmental responsibility into one incredible, fast-growing solution. Then there's strand-woven flooring, which is so tough that it's used in high-traffic commercial spaces like offices, museums, and even airports. Try dragging furniture across that and see if it leaves a mark. It probably won't. And even if it does, a quick sanding can bring the surface back to life. Bamboo is making quiet moves in the industrial world. Inside premium cars, interior panels made from bamboo composites offer lightweight strength and natural beauty, even helping dampen sound. This blend of sustainability and luxury is becoming the new norm. Beyond that, bamboo fibers appear in surprising places. From toothbrush bristles to structural supports in eco-friendly buildings, it's found in biodegradable straws, sleek furniture, and countless products born from innovation. But bamboo's transformation isn't magic. It's a process. One critical step is drying. Done wrong, it can ruin the material. Done right, it ensures strength and durability. Industrial dryers lower moisture from 50% to around 8 to 10%, stabilizing the bamboo for long-term use. Unlike hardwood trees, which take decades to grow and require replanting, bamboo regenerates from its roots. No soil damage, no clear-cutting, no erosion. It simply regrows, making it a champion of sustainability. Properly managed bamboo farms improve soil health, fight climate change by absorbing more carbon dioxide than trees, and support livelihoods without harming ecosystems. It's not just what bamboo becomes, it's how responsibly it gets there that makes it so powerful. On bamboo plantations, local workers often blend traditional harvesting knowledge with modern tools. They carefully select only mature stalks while leaving the young shoots untouched, allowing the cycle to continue uninterrupted. This selective approach keeps the plant regenerating naturally and ensures a long-term sustainable harvest. And there's more innovation on the horizon. Scientists and designers are exploring bamboo's potential in fields like bioplastics, composites, and even medical materials. Experiments are underway to use bamboo fibers in prosthetics, surgical tools, and packaging materials that decompose naturally. No more plastics clogging the oceans. It's no longer just about what bamboo is, it's about what it could become. And the most exciting thing is that this isn't some far-off dream. It's already happening. Of course, none of this works without people, skilled workers across the world, from farmers to technicians to designers, all contributing to the transformation of this humble stalk into a global force. On the plantations, people still walk among rows of towering culms with nothing but machetes, relying on generations of knowledge to choose the right ones to cut. In the factories, workers guide planks into machines that split, shave, boil, and bake them into form. And in the design studios, visionaries imagine what else bamboo can be. Shoes, sunglasses, bicycles, kitchenware, maybe even the next wave of electric vehicle interiors. Every link in the chain matters, and every step reflects how far bamboo has come, from a regional resource to a global game changer. And yet, for all its innovation, bamboo remains humble. It doesn't require fanfare, it just grows. Quietly, efficiently, and incredibly fast. In the right climate, you can actually hear it grow. Some species can shoot up nearly a meter in 24 hours, making them the fastest growing plants on Earth. That kind of growth isn't just impressive, it's game-changing in a world where time and resources are running out. And here's a surprising fact: bamboo is technically a type of grass. Despite its woody appearance and towering height, it's closer to the grass in your lawn than the oak tree in your backyard. But unlike grass, bamboo doesn't stop at a few inches. It keeps going, 30, 40, even 60 feet into the air. And with over 1,000 species, there's a bamboo for just about every purpose, from the tiny ornamental types that decorate living rooms to the giants used for timber and construction. Still, managing this incredible resource takes knowledge. You can't just plant bamboo and walk away. Farmers must know which variety works best for their climate. how to space the culms, when to harvest, and how to care for the rhizome system. With proper care, a single bamboo plantation can provide sustainable harvests for decades. It's the gift that keeps on giving, literally. Now picture this. A factory receives a truckload of 60-foot bamboo stalks. They're green, rough, and full of moisture. By the time they leave the facility, they've been cleaned, stripped, sterilized, dried, pressed, and shaped into products as varied as luxury flooring, soft towels, strong scaffolding, or smooth fabric. It's a full-circle transformation, and it all starts with that first clean cut on the plantation. Now, here's the kicker. The bamboo market is already a giant, and it's only getting bigger. Industry forecasts suggest that the global bamboo economy is heading toward a valuation of over $100 billion. And it's not a bubble, it's a steady climb, powered by real demand, practical innovation, and undeniable sustainability. And while other materials rely heavily on mining, deforestation, or chemical processing, bamboo relies mostly on sunlight, water, and time. That's it. No synthetic inputs, no massive replanting campaigns, just a network of underground roots doing what they do best, regrowing. So what's the catch? There really isn't one as long as plantations are responsibly managed. Overharvesting, monoculture farming, and illegal clearing of natural forests to make room for bamboo crops are real concerns. But with the right balance and oversight, bamboo remains one of the most sustainable resources humans have access to. The story of bamboo is a story of nature's engineering. One plant, fast, strong, beautiful, and versatile, quietly transforming the way we build, dress, furnish, and even heal. And it's just getting started. By now, it's clear that bamboo isn't just a plant, it's a strategy. Nature's blueprint for a better way to build, live, and create. In a time when nearly every industry is rethinking how to cut emissions, reduce waste, and protect the planet, bamboo offers not just an alternative, but a solution that's already proving itself on a massive scale. Every year, over 30 million tons of bamboo are harvested around the world. That's not just a number, it's a reflection of just how deeply bamboo has rooted itself into our modern world. And the growth doesn't stop there. With urban centers expanding, demand for sustainable construction materials rising, and consumer expectations shifting toward eco-conscious products, bamboo is set to play an even bigger role in everyday life. And the beauty of it all? Bamboo doesn't ask much in return. It doesn't demand harsh chemicals. It doesn't ruin the soil. It doesn't even need to be replanted after harvest. It simply grows, renews, and gives back more than it takes. Choosing bamboo over traditional materials sets off a powerful ripple effect. When designers opt for bamboo flooring, they help preserve forests by avoiding the need to cut down trees that took decades to grow. When fashion brands embrace bamboo fabrics, they offer soft, breathable, biodegradable clothing that's gentle on sensitive skin. And when cities use bamboo in construction, they're investing in structures that are both strong and sustainable. Bamboo also brings real-world benefits to communities. It creates jobs in farming, processing, manufacturing, and design, especially in rural areas, while also powering innovation in modern industries. It's not just a fast-growing plant, it's a fast-growing opportunity. But here's what really sets bamboo apart. Hidden inside its fibers is a natural strength-to-weight ratio comparable to steel, flexibility under pressure, and resistance to pests and bacteria. These aren't man-made features, they're natural. Bamboo blends ancient tradition with cutting-edge potential. From scaffolding in Hong Kong to high-end flooring in Europe and eco-luxury fashion in New York, bamboo delivers function, beauty, and sustainability without compromise. It's not just a material, it's a message that we can live smarter, build cleaner, grow without destruction. So the next time bamboo shows up in your life, remember, it's not just good for something, it's good for There's something about diamonds that just stops people mid-sentence. They sparkle like they're alive. They cost more than entire neighborhoods, and yet they're basically fancy carbon. The same element in your pencil tip, just under a ridiculous amount of pressure. Literally. Now imagine this. Somewhere deep under your feet, carbon atoms are having the most intense makeover in history. We're talking temperatures so high your phone would melt just hearing about them. Pressures that would crush steel. And somehow, through all that chaos, the diamond is born. Tiny, perfect, and ready to cause financial heartbreaks across the world. But let's rewind, because before that diamond ends up in a velvet box or on someone's finger during a teary proposal, it's already lived a story spanning billions of years. Yeah, billions. It started about 200 kilometers below the surface, in the Earth's mantle, a place so extreme it makes the Sahara look like a fridge. Down there, carbon atoms start aligning themselves into a crystal lattice, a kind of atomic origami that turns something soft and dull into something nearly indestructible. And no, it's not like diamonds are just sitting there waiting to be picked up. They're trapped, locked away deep underground for millions of years until something wild happens. Volcanic eruptions. Not the fiery, lava-spewing kind that make the news, but ancient eruptions that blasted magma from the depths to the surface. That magma cooled into special rocks called kimberlites. And those kimberlites? They're basically time capsules carrying diamonds from the underworld. That's where humans come in, because of course we do. The moment someone found a shiny stone buried in the dirt and realized it could buy a kingdom, the hunt was on. And that hunt has gotten elaborate. Today, finding diamonds isn't about stumbling upon one in a river like some lucky prospector in a movie. Nope. Geologists are out here using satellites, gravity sensors, and magnetic scanners like detectives following cosmic breadcrumbs. A single grain of kimberlite dust found in sediment can set off a full-blown expedition costing millions. Imagine getting that job. Find the invisible rock that hides the shiny rocks. No pressure, right? Once they locate a promising site, things get industrial. Fast. Open pit mines the size of small cities are carved into the earth in spiral ramps that go down hundreds of meters. And if the deposit is deeper, they dig tunnels that descend nearly a kilometer underground. It's dark, hot, humid, and somehow worth it, because in all that rock, just a few tiny pieces sparkle. On average, you need to dig up 250 tons of rock to get one single carat. One, that's like processing an entire skyscraper's worth of dirt to find a pebble. After extraction, the rocks go through some of the most delicate destruction you've ever seen. Giant crushers grind them down, but with surgical precision. Because while diamonds are famously hard, they're also brittle. Hit them wrong, and congratulations, you've just turned $50,000 into glitter. So everything is done with absurd accuracy. Machines crush just enough to free the diamonds without damaging them. Then comes the wash. Massive drums spinning with high-pressure water, blasting away mud and dust. Out comes a concentrated mix of minerals, and that's when modern tech takes over. See, diamonds have a strange party trick. They glow and hit with X-rays. So conveyor belts carrying crushed rock pass under scanners that detect those tiny flashes. In a split second, a jet of air fires and pops the diamond out of the stream. It's fast, elegant, and weirdly satisfying. Imagine watching hundreds of invisible gems being plucked out of chaos by bursts of air. Somewhere out there, an engineer definitely built that machine just to feel like a wizard. Now the diamonds are free, but they're not exactly glamorous yet. They look rough, cloudy, sometimes like broken glass. So the next phase is sorting, deciding which stones are destined for jewelry and which are going to be turned into industrial tools. About 80% of diamonds actually end up in drills, saws, and cutting instruments because of their toughness. The other 20%? Those are the ones that get to live the high life. And that's when things get seriously technical. Each rough diamond is scanned in 3D down to the micrometer. Advanced software simulates exactly how light will bounce inside it. The program figures out how to cut the stone for maximum sparkle, while avoiding internal flaws that might ruin it. Sometimes a large diamond gets sliced into multiple smaller ones. Other times, the flaws are so minimal that cutters leave it whole, creating those legendary once-in-a-lifetime stones that sell for millions. Cutting itself is a science mixed with art. Lasers make the first incisions clean and precise, Then expert cutters step in with diamond-tipped tools to shape and polish each facet. Fun fact, only a diamond can cut another diamond, so yes, they polish each other, like the world's most exclusive self-care routine. Every angle matters. Every surface has to reflect light perfectly. That signature sparkle people love isn't magic, it's geometry. Mess up one angle and you lose that fire and brilliance that makes diamonds hypnotic. For a master cutter, polishing a single gem can take weeks. Imagine spending a month perfecting something the size of a raisin, knowing one wrong move could ruin it forever. Once the cutting is done, it's time for certification, the diamond world's equivalent of getting a passport. Stones are sent to labs like the GIA or IGI, where they're tested for authenticity and graded based on the 4 C's: carat, color, clarity, and cut. Each stone gets a microscopic code laser engraved on its girdle. You can't see it with your eyes, but it's there, proof of origin and quality. At that point, the diamonds leave the labs and enter a whole new world: luxury. Jewelers like Tiffany, Cartier, and Harry Winston take these tiny marvels and design settings that make them sing. Rings, necklaces, crowns. Each one is a mix of art, engineering, and ego. A diamond never stands alone. It's always paired with a story, a gesture, a meaning someone paid a fortune for. But as bright as the story shines, there's a darker side that refuses to be ignored. In some parts of the world, like Sierra Leone, Angola, or the Central African Republic, diamonds have fueled wars, funded militias, and left behind unimaginable suffering. These are what the world calls blood diamonds, and the irony is painful, a symbol of love and commitment born out of exploitation and violence. Thankfully, global awareness and traceability systems are starting to make a difference. Buyers now demand ethical sourcing, and certifications like the Kimberley process aim to keep conflict stones out of the market. Still, it's a reminder that behind every sparkle is a history, sometimes beautiful, sometimes brutal. Yet humanity doesn't stop at dark truths, it innovates. Scientists looked at all this and said, you know what, let's just make our own. And thus lab-grown diamonds became a thing. Lab-grown diamonds are one of those things that sound fake until you realize they're very real, and they're shaking up an entire industry. These aren't cheap knockoffs or fakes like cubic zirconia. They're chemically, physically, and optically identical to natural diamonds. The only difference? Instead of taking 1 billion years under the Earth's crust, they take a few weeks inside a machine that basically recreates the planet's mantle. There are 2 main ways to do it. One is called HPHT, short for high pressure, high temperature, which is exactly what it sounds like. Scientists take a tiny diamond seed, place it in a chamber, and blast it with around 1,500 degrees Celsius of heat and pressure so high they could crush a tank. Layer by layer, carbon atoms start bonding, building up a diamond crystal just like nature does it, but way faster. The second method, CVD, or chemical vapor deposition, sounds even crazier. Imagine a futuristic tanning bed. Except, instead of giving you a tan, it grows diamonds. Inside a vacuum chamber, methane gas is heated until it releases carbon atoms. Those atoms slowly settle on a flat diamond plate, forming a new crystal over several weeks. What you end up with is a pure, flawless diamond. No dirt, no imperfections, no need to dig a hole the size of a stadium. And guess what? These lab diamonds are so good that even experts often need advanced equipment to tell them apart from natural ones. They look the same, shine the same, and cut the same. Some even argue they're better. Guilt-free sparkle, no environmental destruction, no human exploitation. The only people who aren't thrilled are the ones who make money from digging them out of the ground. But science didn't stop there. Some companies took things in an emotional direction. They now offer what they call memorial diamonds, stones grown using the carbon from a loved one's ashes. Think about that. You can literally turn a memory into something eternal. It's strange, beautiful, and slightly eerie, but it proves how deeply intertwined diamonds are with our emotions. Because here's the truth. Diamonds have always been more than just carbon. They've been symbols for strength, for eternity, for love that supposedly never fades. thanks to one of the most successful marketing campaigns ever. Back in 1947, the diamond company De Beers came up with a slogan that changed everything. "A diamond is forever." Those 4 words transformed an ordinary crystal into the ultimate symbol of romance. It wasn't just an ad, it was psychological alchemy. Before that campaign, diamond engagement rings weren't a thing. After it, they became the thing. Generations grew up believing a proposal wasn't real without one, and De Beers laughed all the way to the bank. That's the wild part about diamonds. Their story is half geology, half human imagination. Nature made them rare and beautiful, but it was people who decided what they meant. From royal crowns to red carpet necklaces to lab-grown keepsakes, every diamond tells a slightly different version of the same story. We crave permanence in a world that constantly changes. Now let's circle back to the production side, because the numbers are almost absurd. Global diamond mining produces roughly 120 million carats a year. That's around 24 tons of diamonds. So next time you see a diamond glittering under a store light, think about where it's been. From carbon atoms trapped 200 kilometers below the Earth to the chaos of volcanic eruptions, through billion-dollar machinery, laser-guided cutters, and ethical debates, all that just to end up on a ring or a pendant. That sparkle isn't just light. It's a history lesson compressed into a single shimmer. And maybe that's why even after centuries of mining, marketing, and man-made alternatives, we still can't look away. Because deep down, every human, whether in a mine, a lab, or a luxury boutique, is searching for something that lasts forever. So if you've enjoyed diving into the world beneath the sparkle, stick around for what's next. A small piece of uranium about the size of a grape has the power to generate enough energy to light up an entire neighborhood for a year. That might sound almost unbelievable at first, but it sparks the question, how can something so small contain such enormous power? The journey of enriched uranium is not just a story of science, it's a story of history, engineering, discovery, and the shaping of the modern world. To understand it fully, let's take a deep look at how this rare and dangerous metal is mined, processed, transformed, and finally used to power cities across the globe. The story begins in the late 19th century, when uranium wasn't considered particularly special. It was in 1896 when French physicist Henri Becquerel made an astonishing observation. Uranium emitted invisible rays all on its own, without sunlight or any external source. This was the birth of radioactivity as a concept. His work inspired Marie and Pierre Curie, who dedicated their lives to studying these strange emissions and discovered entirely new elements like radium and polonium. Just a few decades later, in 1932, James Chadwick identified the neutron, a subatomic particle that would prove critical to unlocking nuclear energy. Then in 1938, Otto Hahn and Fritz Strassmann, with vital input from Lisa Meitner and Otto Frisch, demonstrated something that seemed almost like science fiction. A uranium atom could split in two when struck by a neutron, releasing a burst of energy far greater than anything seen before. This process became known as nuclear fission, and from that point forward, uranium was no longer just another mineral. It became the key to an entirely new form of energy. But there was a complication. Natural uranium mostly contains uranium-238, about 99.3% of it in fact, which does not easily undergo fission. Only a tiny fraction, around 0.7%, is uranium-235, the isotope that makes nuclear energy possible. To make uranium practical for reactors or weapons, the amount of uranium-235 must be increased. This process is called enrichment, and it quickly became one of the greatest scientific and technical challenges of the 20th century. During the Manhattan Project in World War II, scientists pioneered the first methods. They tried gaseous diffusion, which forced uranium gas through thin membranes so that lighter isotopes could be separated, and electromagnetic separation, which bent ionized particles through magnetic fields to pull apart isotopes. These worked, but they were slow and devoured enormous amounts of energy. In the 1950s, a breakthrough came with the invention of the gas centrifuge, a machine capable of spinning uranium gas at staggering speeds and separating isotopes with far greater efficiency. These devices became so critical that their blueprints were guarded like national treasures, considered state secrets by governments around the world. What made enrichment such a turning point was that it shifted uranium from being just a scientific curiosity into a practical source of controlled power. The ability to enrich uranium-235 meant that reactors could be designed with predictable outputs instead of unstable reactions. It also allowed governments to unlock the enormous destructive power of nuclear weapons, changing global politics forever. The very idea that spinning cylinders of metal invisible to the public eye could determine the balance of power between nations gave enrichment a near mythical aura. Engineers working on these systems often describe the centrifuges as temperamental giants capable of incredible precision but unforgiving if mishandled. Even a small technical flaw could bring an entire cascade of machines to a halt, yet when operating smoothly, they represented one of humanity's greatest engineering achievements, blending chemistry, physics, and high-strength materials into a single system. This was the point where uranium became not just an element of the Earth, but a cornerstone of the atomic age. In 1951, the potential of enriched uranium was put to the test when the experimental breeder Reactor 1 in Idaho lit up 4 small light bulbs, the first electricity ever produced from atomic energy. Just 3 years later, in 1954, the Obninsk power plant in the Soviet Union became the first station to connect nuclear power to the electrical grid using uranium enriched to around 5%. This was the dawn of civilian nuclear energy. Today, enriched uranium provides about 10% of the world's electricity, a remarkable achievement that shapes the lives of billions. But how exactly does uranium move from being a rock buried deep underground to becoming the polished fuel that powers reactors? The journey begins in some of the most remote landscapes on Earth: vast deserts in Australia, open plains in Kazakhstan, and rocky terrains in Canada supply about 70% of the world's uranium. Here, the element is locked inside minerals like uraninite, often called pitchblende. These ores may only contain uranium in concentrations as low as 0.1%, sometimes up to 2%, but that small fraction is enough to fuel nations. To extract it, massive excavators carve away layers of earth in open-pit mines, exposing the rock for processing. In other regions, miners tunnel deep underground, sometimes hundreds of meters below the surface, to follow uranium-rich veins. There is also an innovative method called in situ leaching, where chemical solutions such as sulfuric acid or carbonates are injected into the ground to dissolve uranium directly from the deposits. The dissolved uranium is then pumped back to the surface, sparing the need to dig giant pits or tunnels. No matter the method, once uranium is extracted, it must be transported to processing facilities for the next stage. At these plants, the ore is crushed until it resembles coarse sand, a texture that allows chemical treatments to separate uranium from the other minerals it is mixed with. The crushed ore is then placed into large steel tanks and mixed with strong acids or alkalis that leach out the uranium. What emerges from this complex process is a bright yellow powder called yellowcake, or uranium oxide. Despite its harmless appearance, this powder contains about 80% pure uranium. It has a faint metallic smell, and while its radioactivity is relatively low, it is still dangerous to breathe in, so workers wear protective suits, masks, and use specialized ventilation systems. To give a sense of scale, 1 ton of yellowcake can produce the same amount of energy as several million tons of coal. It is at this stage that uranium truly starts to reveal its extraordinary energy potential. From the processing plants, yellowcake is sent to conversion facilities. Here, it is transformed into a chemical compound called uranium hexafluoride, often abbreviated as UF6. This compound is especially important because it can switch between solid, liquid, and gaseous states at relatively low temperatures, which makes it perfect for the enrichment process. Conversion begins with purification, removing impurities like sulfur, magnesium, or other trace metals. The purified uranium is then exposed to hydrofluoric acid in sealed reactors, producing uranium hexafluoride gas. At room temperature, it can solidify into crystals that technicians sometimes call nuclear snow because of its pale greenish appearance. It's a compound that requires extreme care as it reacts violently with water to form toxic substances. For this reason, conversion plants are equipped with corrosion-resistant equipment, advanced ventilation, and sensors that can detect even the smallest leaks. Now comes the most critical step of all: enrichment. Uranium hexafluoride gas is fed into tall cylindrical machines called gas centrifuges. These centrifuges are technological marvels made of ultra-strong alloys and carbon composites. They spin at over 50,000 revolutions per minute inside vacuum chambers that reduce friction. As the gas spins, centrifugal force pushes the heavier uranium-238 isotopes outward while the slightly lighter uranium-235 collects closer to the center. This separation process is delicate, and even the tiniest imbalance, just a few milligrams of weight, can damage the centrifuges. To prevent this, each one is monitored by seismic sensors and real-time control systems that adjust their speed with incredible precision. A single centrifuge can process tons of uranium hexafluoride in a year. But enrichment facilities don't just use one machine. They use cascades, hundreds or even thousands of centrifuges connected together, each one making the uranium a little bit richer in U-235. These cascades often fill entire buildings and run non-stop for decades, producing uranium enriched up to around 5% for commercial reactors. The enriched uranium gas is then converted back into a solid form. Through carefully controlled chemical reactions, it is turned into uranium oxide powder once again. This powder is pressed into small, dense pellets, each one about the size of a fingertip. Despite their tiny size, these pellets are powerful. One of them contains as much potential energy as a ton of coal. To make them reactor-ready, they are baked in furnaces heated to around 1,400 degrees Celsius. Forming tough ceramic materials that can withstand the intense heat and radiation inside a nuclear reactor. The pellets undergo strict quality control. X-rays scan for microscopic cracks, laser scanners measure dimensions to micrometer precision, and spectrometers check for impurities that could interfere with nuclear reactions. Once approved, the pellets are stacked inside long tubes made of zirconium, a silvery metal that resists heat and corrosion while allowing neutrons to pass through. Each tube or fuel rod contains around 400 pellets stacked precisely. Robots handle this process inside clean chambers to avoid contamination. Finally, dozens of fuel rods are bundled into fuel assemblies, carefully welded and tested until they meet exacting standards. These assemblies weigh around half a ton each, and just one of them can power 100 homes for an entire year. When the assemblies reach a nuclear power plant, they are placed inside the reactor core. A single reactor might hold nearly 500 of these assemblies, totaling thousands of fuel rods. Here, the magic of nuclear energy truly begins. Inside the core, uranium-235 atoms split apart when struck by neutrons, releasing tremendous amounts of heat and more neutrons that sustain a chain reaction. The energy released by splitting just one uranium atom is millions of times greater than burning a single carbon atom in coal. To keep the reaction under control, control rods made of materials like boron or cadmium can be lowered into the core. These rods absorb neutrons and act like brakes, slowing or stopping the reaction when needed. The entire system is surrounded by reinforced concrete walls, some as thick as 2 meters, designed to withstand natural disasters or even direct impacts. Inside, automated systems monitor temperature, pressure, and neutron activity constantly, ready to shut everything down if the slightest irregularity is detected. The heat generated from fission doesn't just sit in the core. It is used to boil water, creating steam under high pressure. This steam is channeled into massive turbines that spin at nearly 1,800 revolutions per minute. The turbines are connected to giant generators, which transform the mechanical motion into electricity. A single reactor can produce more than 750 megawatts of power, enough to supply 500,000 homes with electricity. Unlike coal plants, which spew smoke and ash, nuclear reactors emit almost no carbon dioxide while operating, making them one of the cleanest large-scale energy sources available today. Make sure to give the video a like, share it with someone who loves science and technology, and subscribe for more content like this. What are your thoughts on the role of nuclear energy in the future? Leave a comment below, and let's continue the conversation. Gold, humanity's oldest obsession, a metal so rare, so incorruptible, it's been worshipped, fought over, stolen, and locked away behind more security than most nations' nuclear codes. It's said that nothing is harder to fake or more fiercely guarded than a single bar stamped with those 4 shining nines, 99.99% pure gold. But inside one of America's most secretive gold refineries, hidden beyond layers of steel doors and biometric locks, lies a process so meticulous, so demanding, that even the tiniest error could shake the world's faith in the very foundation of value. Because here, in this fortress of science and secrecy, ordinary earth, dull, muddy, veined with quartz and copper, is transformed into something so flawless it can trigger billion-dollar trades with a single test, and it all begins deep underground. The story of gold doesn't start in vaults or markets, it starts in dirt. The raw gold ore that reaches the refinery arrives by the truckload, packed tight with quartz, iron, and streaks of copper. It doesn't glitter, it doesn't shine. To most eyes, it doesn't even look valuable. But hidden inside these rough, jagged stones are microscopic flecks of gold, sometimes less than 1% by weight, locked away inside a dense, tangled web of minerals. The first step is liberation. The ore is fed into giant steel crushers that thunder like mechanical beasts, grinding the rock down until it's nothing but a fine, gray-brown powder. The air fills with dust as massive rotating drums reduce centuries-old earth into something that looks almost like sand. Then comes water, gallons of it, turning that dry dust into a thick, muddy slurry. It's not glamorous, but this slurry holds the promise of fortune. Now comes chemistry's turn to work its magic. The slurry flows into a series of massive tanks where operators introduce sodium cyanide, carefully measured between 100 and 500 milligrams per liter. It sounds dangerous because it is. Cyanide, one of the most lethal chemicals known to humankind, but also one of the only substances that can gently coax gold out of rock. The cyanide bonds with the gold, forming a gold cyanide complex that dissolves the metal atom by atom. It's slow, deliberate, a process that can take 24 to 48 hours as the slurry moves from one tank to the next, each designed to extract every last trace of gold. Operators monitor it constantly. Temperatures, concentrations, flow rates, every variable matters because even a fraction of a percent lost could mean millions of dollars gone. Then, when the gold is dissolved, activated carbon is added, black porous granules that act like sponges for precious metal. The gold molecules cling to the carbon, separating from the waste solution. That's when the mixture is pumped through filters, stripping away impurities. What's left behind is concentrated, 85 to 90% pure, a dull grayish gold powder that marks the end of the chemical phase. But this is just the beginning of transformation. To reach perfection, gold must meet its oldest ally, fire. Inside the refinery's induction furnaces, electromagnetic coils heat the concentrate to more than 1,100 degrees Celsius. It's a mesmerizing sight. The powder liquefies into molten gold, its surface shimmering with traces of copper and silver that haven't yet surrendered. Operators watch from behind heat-proof glass and thick shields as the liquid metal churns and glows like a living thing. When the temperature stabilizes, the furnace tilts, slowly, carefully, releasing a glowing stream of molten gold into heavy steel molds. Each mold is designed for bars weighing between 25 and 40 pounds. The sound is deep like thunder muffled under stone as gold meets steel. Each bar is immediately tagged and logged. The tag isn't just paperwork, it's the bar's DNA, recording where it came from, when it was melted, and the batch details that will follow it through every step ahead. From this moment on, accountability becomes part of the metal itself. The air in the foundry vibrates with heat, carrying the faint metallic scent of something ancient being reborn. Sparks dance across the floor as the operators move with practiced precision, their movements timed like choreography in a ritual that's as much art as science. Every flick of a switch, every measured pour, speaks of generations of refinement handed down through silent discipline. The molten gold pulses with a rhythm of its own, waves of orange light washing over steel walls and mirrored visors. The room hums with low-frequency energy from the induction coils, an invisible current weaving power through every particle of the metal. In that moment, the boundary between nature and engineering blurs. Raw matter yields to order. Earth's hidden treasure finally bends to human design. Sensors embedded in the furnace walls monitor temperature and conductivity, feeding streams of data to control consoles that watch every second of the transformation. Even a single degree out of range could spell disaster. Operators don't shout here. They communicate through hand signals, calm and deliberate, knowing precision is everything. When the pour is complete, the room dims slightly. The glow of the molds becomes the only light, shimmering like captured sunlight solidifying into form. The temperature begins to fall, slow and steady. A faint crackle echoes as the gold shrinks, just enough to free itself from the mold's grip. Steam curls upward, twisting like smoke in an ancient temple. The bars, now cooling on a steel rack, radiate warmth long after the flames fade. Every movement feels ceremonial, every sound deliberate, the heartbeat of a process that defines purity itself. And as the last trace of molten light fades, the bars harden into their first true form, heavy, perfect in potential, waiting for the next stage of transformation. But the leap from rough doré to 99.99% purity requires something extraordinary: electrochemistry. Inside the heart of the refinery stands a row of electrolysis cells, rectangular tanks lined with acid-resistant polymer. The air hums with a faint electrical charge. Here, the true transformation begins. Doré bars are cut into slabs and suspended in the tanks as anodes. Facing them are thin sheets of pure gold, serving as cathodes. Both are lowered into a warm bath of chloroauric acid, held at precisely 70 degrees Celsius. Then, a gentle current of 2 to 3 volts flows through. At this moment, gold dissolves from the anode atom by atom, crossing the liquid in invisible motion and depositing itself onto the cathode in flawless, uniform layers. Every impurity, silver, copper, platinum, sinks to the bottom as a dense gray sludge known as anode mud. But this mud isn't waste. Hidden within it are traces of other precious metals that will later be extracted in separate refinements. The entire room glows faintly blue, illuminated by the quiet pulse of electricity weaving through rows of tanks. The hum of current is steady, like a distant heartbeat, vibrating through the metal frames and tiled floor. A thin veil of vapor drifts above the cells, where chemistry and precision engineering merge in near silence. Operators stand watch, their eyes flicking between readouts, voltage, temperature, ion flow, every number carrying the weight of value itself. The air smells faintly of ozone and acid, sharp but clean, a scent that signals control rather than chaos. The process looks almost tranquil, but beneath that calm surface, millions of atoms are in motion, separating, aligning, reforming. Each second, a microscopic layer of perfection is built, invisible to the naked eye but vital to the bar's ultimate purity. It's a transformation that demands patience. No shortcuts exist here. The bath must remain perfectly balanced, too strong, and the gold corrodes, too weak, and the deposit falters. Every few hours, technicians test samples, ensuring that no unexpected elements sneak through. Even the light in the room is calibrated, cool, white, and uniform to minimize interference with visual inspections. To an outsider, the process might seem repetitive, but to those who understand it, it's a symphony of chemistry, guided by human discipline and trust in the unseen. The surface of each cathode begins to shimmer faintly under the light. Slowly, day by day, it thickens, layer after layer of purity forming silently in the solution. The gold takes on a color that's softer than sunlight, yet heavier than any glow known to man. It's gold in its most perfect state, untouched by imperfection, shaped by electricity itself. After 24 to 48 hours, the cathodes emerge coated in delicate gleaming sheets, 99.99% pure gold. The kind of purity that no chemical or fire alone can achieve. These thin sheets are collected, rinsed, and dried before being remelted once again, this time to perfection. Back in the induction furnaces, temperatures soar to nearly 1,200 degrees Celsius. This final melt isn't about removing impurities anymore, it's about achieving uniformity. The gold must flow flawlessly, filling every corner of precision-engineered molds without air pockets or cracks. As the molten metal settles, a hush fills the room. The glow fades, the bars solidify, smooth and unblemished, ready for testing. But even here, nothing is taken for granted. Each bar must prove itself. In the assay lab, technicians in white coats and gloves begin with X-ray fluorescent scanning. The test is quick, non-destructive, and capable of detecting the slightest impurity, even as low as 0.001%. The numbers flash on digital screens. Anything outside tolerance is immediately flagged. The room feels almost sacred, bright, silent, and precise. Stainless steel counters gleam under white light as instruments hum with quiet authority. Every movement is deliberate, every measurement exact. The technicians barely speak, communicating instead through gestures and data readouts. Then comes the fire assay, an ancient test that remains the world's ultimate judge of gold's purity. A small sliver from a sample bar is placed in a clay cupel and subjected to blistering heat. Every non-gold element burns away. What's left is pure gold, weighed and measured to microscopic precision. Only when both tests agree, the modern and the ancient, does the bar earn its mark. Each one is stamped with weight, fineness, and a unique serial number before being logged into global registries that track its journey from ore to bullion. Every bar becomes part of a legacy of trust. But trust alone isn't enough in the world of gold. Inside the West Point Mint, security operates on a level that borders on science fiction. The vault doors here weigh 21 tons each. No single person can open them. Access requires multiple key holders, biometric scans, and cross-verification from control rooms. Every entry and exit is recorded, audited, and reviewed. Inside, the air is cool and dry, the temperature and humidity held constant to protect the bars from even microscopic change. Each gold bar is non-magnetic, traceable, and subject to random inspections. Nothing leaves these walls without verification. Because in the world of gold, certainty is everything. A single impurity, a single fake, a single breach in trust could ripple through markets, collapsing confidence overnight. And that's not theory, it's history. In 2012, counterfeit bars filled with tungsten appeared in New York, so precisely made they fooled experienced traders. In 2020, thousands of suspect bars from Congo turned up with forged refinery marks. And in 2023, Dubai Customs seized over $60 million in gold-plated fakes, caught only through X-ray and ultrasonic scans. Each of those moments sent shockwaves through the market. Because gold's value isn't just in its shine, it's in the proof that what you're holding is real. To stay ahead of deception, modern refineries have turned to new defenses: high-frequency ultrasound testing, RFID chips, and blockchain tracking. Every legitimate bar now carries its own digital fingerprint, etched by laser and stored across international databases. This means that every piece of 99.99% pure gold produced in America today can be traced back to the exact furnace, the exact batch, even the exact moment it solidified. Every ounce of trust or earned, not assumed. And while digital currencies rise and fall and markets fluctuate, gold remains what it's always been, the benchmark for value itself. Its brilliance is more than beauty, it's a promise forged in chemistry, tested in fire, and locked away behind the heaviest doors ever built by human hands. Because when the world wavers, gold endures. It doesn't rust, it doesn't corrode, it doesn't change. It simply waits, nadita, flawless, untouchable, eternal. And that's how 99.99% pure gold is made inside America's most secret factory. If this journey inside the hidden world of gold fascinated you, there's a lot more to uncover. The world's most valuable secrets aren't just in what's shown, they're in the processes we rarely see. So if you enjoyed exploring this story, make sure to like, share, and subscribe to keep uncovering the unseen with us. Your support helps bring more hidden worlds and untold processes to light.